Welcome everyone. I'm excited to present you portable switch architecture for eBPF, a work that I have been working on with Mateusz and Jan from Orange. If we look at the end-to-end network architecture, we can see clear benefits of using P4 as a common language to specify network behavior and P4 runtime as a unified control plane. We know that P4 can be already deployed in hardware switches or smart NICs, but P4 can also run on multi-core CPUs. As there are different trade-offs between kernel and user space packet processing, PSA-eBPF, which we present in this tech brief talk, gives an alternative to the already existing P4 DPDK framework. We believe that PSA-eBPF can be either used as a P4 programmable virtual switch or as a P4-based VNF or CNF development framework. And there are certainly many exciting and advanced use cases that can be implemented for end-host networking with P4. And PSA-eBPF gives you a way to program Linux kernel with P4. In this talk, I would like to announce PSA-eBPF, which is a new extension to the eBPF backend of the open source P4 compiler. It implements a feature-rich portable switch architecture that should enable many different use cases. So the PSA-eBPF solution is composed of two components. The first one is the PSA-eBPF compiler, and the second one is a PSA-eBPF API and CLI tool that allows users to load and manage PSA programs that are written for eBPF. The PSA-eBPF workflow does not differ from the basic P4 workflow. A P4 developer must write a P4 program according to a standard PSA model. Then the P4 developer can use the PSA-eBPF compiler provided by us to generate eBPF bytecode. The eBPF bytecode is intended to be run inside the Linux kernel and attached to different network interfaces. However, the management of generated eBPF programs is not so straightforward, and this is why we provided the PSA-eBPF API and also a CLI tool, which can be used by a P4 developer to load and manage P4 programs for eBPF. In a nutshell, PSA-eBPF is a near complete PSA implementation for eBPF. We use the combination of different eBPF data types, primitives, and TC and XDP hooks to map the PSA model to the eBPF subsystem. We verified, designed, and implemented all the packet paths that are defined by the PSA specification, so a P4 developer can enforce different packet paths like normal unicast, multicast, packet recirculation, or resubmission. We developed almost all match kinds for P4 tables. The exact and longest prefix match are implemented by using basic eBPF primitives. For ternary matching, we adopted the tuple space search algorithm that is also used by the Open vSwitch solution. And we haven't implemented range matching yet, but this is on our roadmap. All PSA XRs are designed and implemented, so a P4 developer can use a full spectrum of different XRs to implement advanced network applications. We have a pretty good PTF test coverage. Each feature that I mentioned above is covered by a PTF test. We currently run about 70 PTF tests as a pre-merge job. And finally, as I mentioned before, we provide this PSA-eBPF CAPI that can be used by a control plane stack to implement a higher level control plane interface. The goal of this talk is to encourage you to give the PSA-eBPF a try and use it in your projects. To learn more, please watch the extended P4 workshop tutorial that is called Deep Dive and Getting Started with PSA Implementation for eBPF. And we are sure that you will learn a lot of implementation details and how to use different tools to compile, deploy, and run P4 programs compiled for eBPF. Please also visit the official documentation site in the open source P4 compiler repository. To start playing with PSA-eBPF, you can either reproduce the PSA-eBPF demo that we provided that implements a load balancer, rate limiter, and QoS program, or you can integrate PSA-eBPF with Mininet and run the test topology on your laptop. Feel free to reach us out on Slack or report a bug so that we can support your projects. Thank you.